For today's lesson, we want to talk about adding time as another variable, as a parameter, so that we can judge both distance horizontal and vertical as a function of time. In the past, when we say had a baseball player hit a ball or we threw a ball, we could either make a parabola, follow the quadratic, and either chart time and vertical height, or we could chart horizontal distance and vertical height, but we couldn't chart time. So what we want to do today is throw another variable in there, such as time, make it a parameter, and we can watch both the horizontal distance and the vertical height change as a function of time. To do that, we're going to set our calculator. We're going to have to put our calculator in parametric mode. So in your mode, you're going to change this. We're going to change also to degrees. And we're going to change function to PAR, parametrics. When you go into your y equals, you'll get your two sets of equations for this. So now we're going to work on our scenario here. We have a baseball player who hits a ball 3 feet from the ground, that's where he holds his bat, with the initial velocity of 152 feet per second at an angle of 20 degrees. We're going to write a set of parametric equations for the path of the baseball as he hits it. So we have two generalized equations. One, the x deals with anything along the x-axis, and in our case, it will be our horizontal distance. Anything that affects the horizontal distance will be in the x. In the y will be anything that affects the vertical distance. We've got initial velocity, v1, t, this is our parameter for time, the cosine of the angle and the sine of the angle, this is his angle that he's hitting the ball at, wind speed, which we'll add in a minute, so right now we have no wind speed, there's no wind blowing, and in our vertical, we have to use negative 16t squared, so the pull of gravity brings the ball back to the ground. So we're going to set up our equations. We're at initial velocity of 152 feet per second, so since this is dealing with time, we put the t. We want the cosine of our angle, and right now we have no wind speed. Our y equation will start out the same, the sine of 20, and we're going to put the negative 16t squared so that the pull of gravity can bring the ball to the ground. And we also have one more vertical change. He hits the ball not on the ground, but 3 feet above the ground. That's where his bat makes contact with the ball. So we give it a +3. So actually, when we graph this time, we'll start here at the +3, and we'll watch his ball follow a parabolic path. So we're going to enter this in our calculator, and we're going to put them in. If you hit the x bar, you get the t. That's why we made sure we were in degrees, and we put it in parametric mode. And then we're going to come down and set your y up as well. Same setup, function of time, sine, minus the 16t squared. This will bring our ball back down, gravity, +3. Now, if I just graph this, it looks a little strange because it's not really set up for my parametric graph. So I can look at my table and know that if I started this at 0 and I incremented by 1, it probably takes 5 or 6 seconds, somewhere in here, before the ball hits the ground. And we can tell by the y distance when the ball hits the ground. So this is a nice way to set up your table. Time is going to go, and it doesn't have to be exact, from 0 to, let's make it 6, and use a t-step of 0.5. X is also at 0, there's no negative distance, and maybe our x goes to 600. And y is going to go from 0 to its max, probably about 80, somewhere in there. You're just setting up a window. So we're going to change your window. close on this one for my time step. So make your mins be 0. Oops. Make your mins be 0 because it's an application. Your x max, we made it be 600. We need to see that parabola turn. Your y min 0 and maybe 180, whatever you would like to make this. It's just a window. So now we can see the path of our ball. We want to trace this. We're going to draw this sketch. It starts at the 3 and comes down and eventually hits the ground. And we're going to have to trace that ball. Now, as we do this, we're going to see that will this ball clear a 10-foot fence at 440 feet? He's going to hit a home run. The home run fence is 440 feet away from the batter. Somewhere 440 feet. We want to know there's a fence here. Somewhere along, we don't know exactly where, but there's a 10-foot fence at that height. So not only does he have to make a horizontal distance of 440 feet, he has to make a vertical distance of a little bit more than 10 feet. So we're going to trace it on our calculator. We hit the trace button and we trace. You can see 3 parameters here. You can see your time, you can see your x, and you can see your y. Time is the one that's moving. This is our parameter. It's an interactive variable here. So as our time changes, and I set my time step to 0.5, if you go a little smaller, your graph may not come out as exact or may go a little slower, but you'll get a little closer when you're doing this. But we can always fine-tune if we need to. So we're looking for your x value to hit 440. Now at time of 3, we're at 428. At a time of 3.5, we're at 499. So you can do a calc value on this. Maybe put it at 3.2 and check it. And I'm still a little bit past the 440. I can check it again, go to 3.1. And I'm pretty darn close. And if you notice here, when your time is 3.1 seconds, your x value is 442 feet, 0.73, we'll just round it, and your y value is greater than 10. Do we have to go be a little bit more exact at the 440? No, because we're past the 440 and we were above 10. So if you get this far, you're fine. If you want to fine tune, go to your table, start at the 3.1 and increment it by 0.001. And when you look at it here, you'll be able to find exactly at your 440. Here's my 440. And here's my time, here's my 440, and here's my height. So clearly, he hits a home run. He went the distance of 440 horizontally, and he went a vertical distance of more than 11 feet. So his ball sails over the 10-foot fence and he hits the home run. Now, sometimes the conditions aren't so ideal. Sometimes there's a little bit of wind here. Now, if there's a little bit of wind, his ball is going to change slightly. So we're going to add a little wind to this. We're going to add an 8-mile-an-hour wind to this. And let's make it a little bit more. Let's make it 10 miles an hour. Well, let's make it a little even. Now we have our 2 statements. Nothing changes here. And he's still 3 feet above when he does this. Now wind speed will affect how far the ball travels horizontally. If the wind is with him, it'll push his ball a little further. If the wind is against him, it's going to hold his ball up a little bit. Now, notice it is also a time variable. So that's where our parameter comes in t. However, we have one other problem. This is given in miles per hour. Our velocity was given in feet per second. So we have to convert from miles per hour to feet per second. In 1 mile, there are 5,280 feet. In 1 hour, there are 60 minutes times 60 seconds. There are 3,600 seconds. So we're going to multiply 10 times 5,280 and divide it by 360. And we'll get approximately 14.67 feet per second. That's how fast your wind is traveling at. That's the speed of your wind. Now, since the wind affects the horizontal, we're going to change the x equation. And since it works against the batter, we're going to subtract it from here. Since it is also a function of time, we need our t parameter. And we're going to see what happens. We should get the same look to this. However, it should stop a little sooner than before. So let's see by adding this what happens. So we're going to our y equation. Our y is good. We're going to change our x, our xy equations. We're going to change our x, and we're going to subtract our new wind speed. And it is a function of time. Don't forget the t. So the overall graph looks good, but I don't know if you noticed, we're a little further in right here. So now we're going to trace again, and we're going to look, when is x? 440 feet. He still needs to make the home run, and he still needs to clear the fence. So we're going to trace until we see 440. So we're about 448. We're a little bit, probably a little bit before 3.5. So again, we have our table set it at 3.5, and increment it by 0.001, and we can get exactly 440. If you find it's too far for you to flip through, reset your table set. Start it at a lesser time, and you'll get there. This wasn't so bad. You can get there. Now, because the wind is working against him, notice when he's 440 feet away, his ball is below the ground right now, technically. So he does not clear the distance of the 10-foot fence. So if the wind speed is working against him, he does not have a home run. There is no home run. He probably got a nice little hit in the outfield, but he didn't get a home run. So adding another variable to your function allows you to actually trace the time as well. How many seconds does it take, your horizontal distance, and your vertical distance. It's a nice interactive approach to graphing. Anything that, especially that follows a quadratic or a parabola movement here.